In the vast expanse of the universe, an inquiry into the contents of a black hole is a query of immense value, akin to a fortune of $1 trillion. Another way to describe a black hole is available. As per the holographic description, there exists a two-dimensional realm that envelopes every three-dimensional world. This two-dimensional world possesses identical physics to the three-dimensional world we know, but it portrays it in an entirely distinct language. The gravitational force exerted by black holes is incredibly powerful, distorting not only the space and time in their vicinity, but also light and information. The pull of the black hole is so intense that nothing can break free from its grasp. In simpler terms, the holographic technology. The enigmatic nature of black holes in the cosmos stems from the lack of information surrounding their conception. According to current physics theories, the interior of a black hole is a location where matter is compressed to an infinitely small point. Within this singularity, time, space, and our understanding of physics cease to exist. But what if the singularity transcends being a mere infinitesimal point of nothing and everything? The question arises, could it be a wormhole linking two universes or two distinct locations within our own universe? What if every black hole, looming in the vast expanse of space, held within it a mystery that we may never fully comprehend? Welcome, the AWZ News. And today, let's find out what scientists have found inside a black hole. Don't forget to subscribe our channel. Thanks to the contributions of brilliant minds such as Albert Einstein and Stephen Hawking, we possess a significant comprehension of the occurrences that take place outside of a black hole as an object draws near to the event horizon, which is commonly referred to as the notorious point of no return. As an object draws near the event horizon, its escape velocity surpasses the speed of light. Consequently, all forms of light become ensnared in the gravitational pull of a black hole. At this point, physics appears to disregard its own principles, resulting in a scenario where even light is incapable of evading the immense gravitational force of a black hole. Jeremy Barami. On the afterlife timeline, a new discovery has been made thanks to the power of quantum computers. This discovery sheds light on the nature of the ever-craving behemoths that are the main attraction of almost every known galaxy. Imagine being told that the most terrifying entities in our universe, the Baba Yagas of the cosmos, are merely figments of our imagination. It is not being stated that the entities in question will vanish if one ceases to believe in them. The research team, led by Enrico Rialdi, has conducted simulations, and the University of Michigan's research team is proposing a more complex solution. As the observer gazes upon the black holes, they seem to take on the form of uncomplicated holographic projections. The term hologram, in this context, is not referring to the holograms commonly seen in science fiction movies such as Star Wars. Instead, it is being used in a more scientific manner. The concept revolves around holographic duality, a mathematical hypothesis that endeavors to link theories concerning particles and their interactions with the theory of gravity. The language used was too complex for the listener to understand. The speaker suggests simplifying the task at hand. The crux of the matter lies in the absence of a comprehensive theory that can provide a coherent explanation for the entirety of the universe. In one corner, we have Einstein's general relativity theory, which posits that space-time is the only existing entity and particles do not exist. This theory operates in the third dimension. On the other hand, the standard model of physics concerns itself with particles and disregards gravity entirely. As far as black holes are concerned, they are described in the second dimension. The two theories are both pertinent in their depiction of their operations. However, physics has been grappling with a persistent challenge since the previous century, reconciling the two theories. Here is where Rialdi and his team may have achieved success. They employed quantum matrix models and linked the two theories, allowing them to explore holographic duality using their knowledge of particle theory and gravity theory. By utilizing the models developed within the framework, the researchers were able to conduct simulations that shed light on the potential appearance of gravity within a black hole. The current understanding of the interior of a black hole is rooted in the theory of gravity. This theory suggests that the black hole causes space and time to shift in and out of its center. The idea of using simple matrix models composed of blocks of numbers was conceived by the researchers. From that point on, the user could commence crafting various items utilizing the framework employed in quantum computers. The calculations indicate that the optimal approach to understanding the inner workings of a black hole is to compare it to a holographic projection. However, it is unclear how the researchers came to this surprising conclusion. Firstly, let us understand what a hologram means in this particular context. In this scenario, the term hologram is used to describe a flat image or picture that can be projected into the third dimension. At the 2014 Billboard Music Awards, Michael Jackson was resurrected as a hologram and performed Slaves to the Beat. Meanwhile, researchers were exploring the relationship between the theory of gravity and particle theory using quantum matrix models. Through their work, they attempted to describe a black hole as a three-dimensional entity that we perceive through two-dimensional particles, although this explanation is not entirely precise. Through the use of quantum matrix models, researchers have been able to explore the relationship between the theory of gravity and particle theory. This is not the first attempt to predict the inner workings of a black hole through mathematical equations. In a specific mathematical case, astrophysicists have determined that the singularity inside a black hole is not a point but rather a ring. This is due to the centrifugal force that causes the horizon of the black hole to bulge out into an ellipse, which in turn opens the singularity into a ring. The outer and inner horizons of the black hole form confocal ellipsoids, with the ring's singularity located at the focus of the ellipsoid. However, it is important to note that this mathematical scenario does not necessarily reflect reality. Other calculations in the past proposed that the singularity is actually a whole surface inside the event horizon. We just don't know. It could be that in real black holes singularities don't even exist and the spacetime singularity is inevitable, and the picture I've drawn doesn't capture a key feature of spacetime singularities, and the key feature of spacetime singularities inside black holes is that their singularities in time are not in space. There is also a theory that suggests that deep inside a black hole matter doesn't get squished down into that infinitely tiny point called a singularity. Instead, it might exist as the tiniest possible pocket of volume, which could be the smallest possible configuration of matter. If a singularity was a point in space, let's imagine it was in the center of this room, you have this strong sense that you should be able to avoid it if you find your rockets. Surely I could just move away from the spacetime singularity. Why do I have to hit the spacetime singularity? That's true, and that's because spacetime singularities and black holes are not of that form. The spacetime singularity is a singularity in time, and you should think of a moment in time in the future that you can't avoid. This would be a Planck star, and it's a theoretical possibility envisioned by loop quantum gravity, which is itself a highly hypothetical proposal for creating a quantum version of gravity in the world of loop quantum gravity. Quantum gravity, space and time are quantized, and the universe around us is composed of tiny discrete chunks, but at such an incredibly tiny scale that our movements appear smooth and continuous until we find a way to extract information from the bowels of a black hole. We won't really truly be sure if what we're seeing is all there is to see in 2D, 3D, or beyond, and if the most recent calculations turn out to be correct, then that begs an existential question: if the black holes are a hologram, what about the rest of the universe? Well, at this moment, there is no clear answer, and so we can say yes and no. Of course, for us, holograms are just two-dimensional images created with lights in a three-dimensional space, but in this case, Rinaldi and his colleagues are referring to the interaction a black hole has with its surroundings universe. On the other hand, is a different case. But what if it was a three-dimensional image projected in four-dimensional space? Would it make a hologram as well? Black holes represent a moment where our universe ends and folds back upon itself, where relativity and quantum physics collide. We just need to find a way how to connect the two moments, and we may find the unifying theory to define the universe. The answer may lie inside a black hole. Do you have the guts to dive into it and find it? Thank you for watching. Don't forget to subscribe our channel.